Okay, hello everyone. Today we will continue to study the protocols in the transport layer. We know the internet has two main protocols in the transport layer. One is UDP, the other is TCP. The connectionless protocol is UDP. UDP does almost nothing beyond sending packets between applications, letting applications build their own protocols on top as needed. The other is TCP. TCP is a connection-oriented protocol. It does almost everything. It makes connections and adds reliability with retransmission, along with flow control and congestion control, or on behalf of the application that use it. So the internet has UDP and TCP in the transport layer. UDP is simple, while TCP can do almost everything. UDP provides reliable service with retransmission, flow control, and congestion control. Then, in the following section, we will study UDP and TCP. We will start with UDP because it is simplest. We will also look at two uses of UDP. Since UDP is a transport layer protocol that typically runs in the operating system, and protocols that use UDP typically run in user space. These uses might be considered applications. However, the techniques they use are useful for many applications and are better considered to belong to a transport service. So we will cover them here. The first protocol is UDP. UDP means User Datagram Protocol. It provides a way for applications to send encapsulated IP datagrams without having to establish a connection. So UDP provides a connectionless service. So without having to establish a connection. UDP is described in the Internet Standard File RFC 768. UDP transmits segments consisting of an 8-byte header followed by the payload. The two ports serve to identify the endpoints within the source and destination machines. This figure shows the header of UDP. So there are 4 fields in the header of UDP. Includes source port, destination port, UDP length, UDP checksum. When a UDP packet arrives, its payload is handed to the process attached to the destination port. This attachment occurs when the bind primitive or something similar is used. In fact, the main value of UDP over just using raw IP. That means what's new of the function of UDP over IP protocol. So the main value of UDP over just using raw IP is the addition of the source and destination ports. So UDP have ports, but IP no ports, right? Without the port field, the transport layer would not know what to do with each incoming packet. With the ports field, it delivers the embedded segment to the correct application. So UDP has the source and destination port field that is useful to the application. The source port is primarily needed when a reply must be sent back to the source. By copying the source port field from the incoming segment into the destination port field of the outgoing segment, the process sending the reply can specify which process on the sending machine is to get it. The UDP length field includes 8-byte header and data. The minimum length is 8-byte to cover the header. The maximum length is 65,515 bytes, which is lower than the largest number that will fit in 16 bits because of the size limit on IP packet. The optional checksum is also provided for extra reliability. It checksum the header, data, and a conceptual IP pseudo header. When performing this computation, the checksum field is set to 0, and the date field is padded out with additional 0 byte if its length is an odd number. The checksum algorithm is simply to add up all 16-bit words in one's complement and to take the one's complement of the sum. As a consequence, when the receiver performs the calculation on the entire segment, including the checksum field, the result should be 0. If the checksum is not computed, it is stored as a 0. Since by a happy coincidence of one's complement arithmetic, a true computed 0 is stored as all ones. However, turning it off is foolish, unless the quantity of data does not matter. The figure 28 shows the IPv4 pseudo header included in the UDP checksum. Pseudo header for the keys of IPv4 contains 32-bit IPv4 addresses of the source and destination machine, source address and destination address of machine. The protocol number for UDP, it is 17 constant, and the byte count for the UDP segment. It is probably worth mentioning explicitly some of the things that UDP does not do. What does not UDP do? It does not do flow control, congestion control, or retransmission upon receipt of a bad segment. All of that is up to the user processes. So UDP is simple. It does not do flow control, congestion control, or retransmission. All of that is up to the user processes. What it does do is provide an interface to the IP protocol with the added feature of demultiplexing multiple processes using the ports and optional end-to-end error detection. That's all UDP does. That's all UDP does. Now, about remote procedural calls, we will not introduce in detail. In a certain sense, sending a message to a remote host and getting a reply back is a lot like making a function call in the programming language. In both cases, start with one or more parameters. You get back a result. This observation has led people to try to arrange request-reply interactions on networks to be cast in the form of procedure calls. Such an arrangement makes network applications much easier to program and more familiar to deal with. For example, just imagine a procedure named get IP address using host name as parameters that works by sending a UDP packet to a DNS server and waiting for the reply, coming out and trying again if one is not forthcoming quickly enough. In this way, all the details of networking can be hidden from the programmer. So programmers can program networking application easily with remote procedure call. RPC means remote procedure call, has become the basis for many networking applications. Traditionally, the calling procedure is known as the client. The called procedure is known as the server, and we will use those names here too. We will not illustrate in detail. Here, figure 29 shows the steps 1, 2, 3, 4, 5. So in the steps, step 1 to 5 in making a remote procedure call. Here the shaded component is steps. Okay, we will not introduce it in detail. Now we will talk about real-time transport protocols, because real-time transport protocols are also based on UDP. In particular, as internet radio, internet telephony, music on demand, video conferencing, video on demand, and other multimedia applications became more commonplace, people have discovered that each application was reinventing more or less the same real-time transport protocol. So it gradually became clear that having a generic real-time transport protocol for multiple applications would be a good idea. Thus was RTP, Real-Time Transport Protocol, born. RTP is described in the Internet Standard File RFC 3550 and is now in widespread use for multimedia applications. We will describe two aspects of real-time transport. The first is the RTP protocol for transporting audio and video data in packets. The second is the processing that takes place mostly at the receiver to play out the audio and video at the right time. These functions fit into the protocol stack as shown in figure 30. For example, look at the subfigure A, shows the position of RTP in the protocol stack. RTP locates in the user space. It is over UDP and provide service for multimedia applications. And the subfigure B shows the packet listing, layered RTP payload, RTP header, RTP payload, means RTP protocol unit encapsulated in UDP, UDP encapsulating IP, IP encapsulated in the MAC, Ethernet MAC. RTP normally runs in user space over UDP in the operating system. It operates as follows. Since multimedia application is widely used, then RTP are also widely used. Multimedia application consists of multiple audio, video, text, and possibly other screens. These are fed into the RTP library, which is in user space along with the application. This library multiplexes the screens and encodes them in RTP packets, which it stuffs into a socket, stuffs in the socket using socket interface, right? On the operating system side of the socket, UDP packets are generated to wrapped RTP packets and handed to IP for transmission over a link such as Ethernet. This is a OS kernel processed in US kernel. The reverse process happens at the receiver. The multimedia application eventually receives multimedia data from the RTP library. It is responsible for playing out the media, the protocol stack for the situation shown in the subfigure A. Okay, the basic function of RTP is to multiplex several real-time data streams onto a single stream of UDP packets. So, although UDP provides unreliable service, but RTP, especially multimedia application, needs UDP. UDP streams can be sent to a single destination or to multiple destinations. Because RTP just uses normal UDP. Its packets are not treated specially by the routers unless some normal IP quantity of service features are enabled. In particular, there are no special guarantees about delivery, and packets may be lost, delayed, corrupted, etc. RTP format contains several features to help receivers work with multimedia information. Here, figure 31 shows the RTP header. RTP header have these fields: version, PXCCM, payload type, sequence number, timestamp, synchronization source identifier, etc. Then here in this slides illustrated the function, the meanings of each field. The version field, which is already at 2, the P bit, just a bit, P bit indicates that the packet has been headed to a multiple of 4 bytes. The last pending byte tells how many bytes were added. Next field is X. X bit indicates that an extension header is present. Then CC, 4 bits. CC field tells how many contributing sources are present, from 0 to 15. M bit is an application-specific marker bit. It can be used to mark the start of a video frame, the start of a word in the audio channel, or something else that the application understands. Then the payload type. Payload type field tells which encoding algorithm has been used. For example, uncompressed, 8-bit audio, MP3, etc. Since every packet carries this field, the encoding can change during transmission. Then the other fields we will not introduce in detail. RTP has a little sister protocol that is RTCP, Real-Time Transport Control Protocol. RTP is a real-time transport protocol. It has a sister protocol, called control protocol. It is defined along with RTP in the Internet Standard Document RFC 3550 and handles feedback, synchronization, and user interface. It does not transport any media samples. Now we will introduce TCP. TCP means Transmission Control Protocol. Was specifically designed to provide a reliable end-to-end byte stream over an unreliable internet network. An internet network differs from a single network because different parts may have widely different topologies, bandwidths, delays, packet sizes, and other parameters. TCP was designed to dynamically adapt to properties of the network and to be robust in the face of many kinds of failures. So TCP provides reliable services. TCP was formally defined in the document RFC 793 in September 1981. As time went on, many improvements have been made, and various errors and inconsistencies have been fixed. To give a sense of extent of TCP, the important RFC document listed here. RFC 1122, RFC 1122 is about clarifications and bug fixes and some extensions for TCP, high performance in RFC 1323, selective acknowledgements in RFC 2018, congestion control in document RFC 2581, repurposing of header fields for quantity of service in RFC 2873, improved retransmission timers in RFC 2988, and ECN, that is explicit congestion notification, in RFC 3168. The full connection is even larger, which led to a guide to the many RFCs, published of course as another RFC document, RFC 4614. The IP layer gives no guarantee that datagrams will be delivered properly, nor any indication of how fast datagrams may be sent. So IP layer have no these functions about reliable transmission, no any indication of how fast datagrams sent. It is up to TCP to send datagrams fast enough to make use of the capacity, but not cause congestion. So TCP should transmit the data as fast as possible, but should not cause congestion. How can TCP do? And to time out and retransmit any datagrams that are not delivered. Datagrams that do arrive may well do so in the wrong order. It is also up to TCP to reassemble them into messages in the proper sequence. In short, TCP must furnish good performance with the reliability that most applications want, and that IP does not provide. So TCP have these functions such as congestion control, flow control, reassemble in proper sequence, good performance, reliability, but should not make the network congest. About TCP service model. TCP service is obtained by both the sender and the receiver, creating endpoints called sockets, as described in the former section. Each socket has a socket number consisting of the IP address of the host and 16-bit number local to the host called the port. So each socket has a socket number consisting of the IP address of the host and the port number of that host, the port number local to that host. So the socket is the combination of the IP address and the port number. A port is the TCP named for TCP, service access point. For TCP service to be obtained, a connection must be explicitly established between a socket on one machine and a socket on another machine. Here, this figure lists some important primitives such as socket, bind, listen, accept, connect, send, receive, and close. This is the backbone of the socket. For example, socket is used to create a new communication endpoints. Bind, associate a local address with a socket, and listen, accept, connect, send, receive. A socket may be used for multiple applications at the same time. In other words, two or more connections may terminate at the same socket. Connections are identified by the socket identifier at both ends, that is, socket 1 and socket 2, that is the two endpoints, the both end of a connection. No virtual circuit numbers or other identifiers are used. Port numbers below 1024 are reserved for standard services that can usually only be started by privileged users. For example, root in Unix system. They are called well-known port. So well-known port is usually for the system process, and they are below 1024. For example, any process wishing to remotely retrieve mail from a host can connect to the destination host port number 143 to contact its IMAP daemon of a mail server. The list of well-known ports is given at this website. Over 700 have been assigned. This figure shows some better-known port numbers. Port 2021 for FTP, 22 for SSH, 25 for email SMTP protocol, 80 for HTTP, etc. It would certainly be possible to have the FTP daemon attach itself to port 21 at boot time, and SSH daemon attaches itself to port 22 at boot time, and so on. However, doing so would clutter up memory with daemons that were idle most of the time. That is, make the efficiency very low. Instead, what is commonly done is to have a single daemon called inetd. Inetd in Unix attaches itself to multiple ports and wait for the first incoming connection When that occurs, inetd forks off a new process and executes the appropriate daemon in it, letting that daemon handle the request. In this way, the daemons other than inetd are only active when there is work for them to do. inetd learns which ports it is to use from a configuration file. Consequently, the system administrator can set up the system to have permanent daemons on the busiest port and inetd on the rest. This is about TCP service model to support several services simultaneously. Now, all TCP connections are full duplex and point-to-point. Full duplex means that traffic can go in both directions at the same time. Point-to-point means that each connection has exactly two endpoints. TCP does not support multicasting or broadcasting. So TCP does not support multicasting or broadcasting, while UDP can support multicasting or broadcasting. That is, they are needed by video conferencing or other multimedia application. A UDP connection is a byte stream, not a message stream. This is the other important feature of TCP. Message boundaries are not preserved end-to-end. For example, if the sending process does full 512-byte writes to a TCP stream, this data may be delivered to the receiving process as 4 512-byte chunks, 2 1024-byte chunks, 1 2048-byte chunks, or some other way. There is no way for the receiver to detect the units in which the data were written, no matter how hard it tries. So there is no way for the receiver to detect the units. That means TCP is a byte stream, not a message stream. It does not preserve the message boundaries. For example, this figure shows the 4 512-byte segment A, B, C, and D, sent as separate IP datagrams. When an application passes data to TCP, TCP may send it immediately or buffer it at its discretion. However, sometimes the application really wants the data to be sent immediately. For example, suppose a user of an interactive game wants to send a stream of updates, it is essential that the updates be sent immediately, not buffered until there is a connection of them. To force the data out, TCP has the notion of a push flag that is carried on packets. The original intent was to let applications tear TCP implementations by the push flag, not to delay the transmission. However, applications cannot literally set the push flag when we send data. Instead, different operating systems have involved different options to expanded transmission. So it depends on operating systems. Let's have a rest for 10 minutes. Okay, let's have a rest for 10 minutes. Please keep connections on to the Tencent classroom. Have a rest for 10 minutes. Okay, this section we will give a general overview of TCP protocols. A key feature of TCP and one that dominates the protocol design is that every byte on the TCP connection has its own 32-bit sequence number. When the internet began, the data rate is very low, with mostly 56 kilobit per second, least nines. So a host bursting away at full speed took over 1 week to search through the sequence number space. The sending and the receiving TCP entities exchange data in the form of segment. A TCP segment consists of a fixed 20-byte header, followed by 0 or more data bytes. TCP software decides how big segments should be. It can accumulate data from several writes into one segment, or can split data from one write over multiple segments. Now, two limits restrict the segment size. The first is it must fit in 65,550 byte IP payload. The other is the Ethernet payload size. So each link has an MTU limitation. The basic protocol used by TCP and is the sliding window protocol with a dynamic window size. When a sender transmits a segment, it also starts a timer. When the segment arrives at the destination, the receiving TCP entity sends back a segment bearing an acknowledgement number equal to the next sequence number it expects to receive, and the remaining window size. If the sender's timer goes off before the acknowledgement is received, the sender transmits the segment again. Segments can arrive out of order. Segments can also be delayed so long in transit that the sender times out and retransmits them. TCP must be prepared to deal with these problems and solve them in the efficient way. A considerable amount of effort has gone into optimizing the performance of TCP streams, even in the face of network problems. A number of the algorithms used by many of TCP implementations will be discussed below. The TCP segment header, it has a fixed format 20-byte header. Every segment begins with a fixed format 20-byte header. The fixed header may be followed by header options. After the options, if any, up to 65,495 data bytes may follow, where the first 20 refer to the IP header and the second to the TCP header. Segments without any data are legal and are commonly used for acknowledgements and control messages. Now, figure 36 shows the TCP header. Source port, destination port, sequence number, acknowledgement number, TCP header length, CWR, ECE, URG, ACK, PSH, etc. This bit flag, window size, checksum, urgent pointer, options field, then followed by data. The source port and destination port fields identify the local endpoints of the connection. A TCP port plus its host IP address forms a 48-bit unique endpoints. The source and destination endpoints together identify the connection. This connection identifier is called a 5-tuple because it consists of 5 pieces of information: the protocol, source IP, source port, destination IP, destination port. Includes 5 pieces of information called a 5-tuple. The sequence number and acknowledgement number fields perform their URL functions. Note that the latter specifies the next in order byte expected, not the last byte correctly received. It is a cumulative acknowledgement because it summarizes the received data with a single number that does not go beyond lost data. Both are 32 bits because every byte of data is numbered. Every byte of data is numbered in the TCP stream. TCP header length tells how many 32-bit words are contained in the TCP header. TCP header length here. It tells how many 32 bits are contained in the TCP header. This information is needed because the options field is of variable length, so the header is 2. Technically, this field really indicates the start of the data within the segment, measured in 32-bit words. Note that number is just the head length in words, so the effect is the same. Next comes a 4-bit field. It's not used. 4-bit is not used. Then some bit flags. CWR and ECE are used to single congestion when ECN is used as specified in RFC 3168. URG is set to 1 if the urgent pointer is in use. The urgent pointer is used to indicate a byte offset from the current sequence number at which urgent data are to be found. The AC key bit is set to 0 to indicate the acknowledgement number is valid. This is the case for nearly all packets. If AC key flag is 0, the segment does not contain an acknowledgement, so the acknowledgement number field is ignored if AC key is 0. Then the PSH bit indicates push the data. RST bit is used to abruptly reset a connection that has become confused due to a host crash or some other reason. It is also used to reject an invalid segment or refuse an attempt to open a connection. SYN bit is used to establish connections. The connection request has SYN set with 1 and ACK set with 0 to indicate that the piggyback acknowledgement field is not in use. The connection reply does bear an acknowledgement, however, so it has SYN1 and ACK1 in sense that SYN bit is used to denote both connection request and connection accepted, with the ACK bit used to distinguish between those two possibilities. Then FIN bit is used to release a connection. It specifies that the sender has no more data to transmit. Then TCP, how does TCP provides flow control and congestion control? It depends on the sliding window mechanisms. Flow control in TCP is handled using a variable-sized sliding window. Window size field here, window size field implement the function of flow control. This window size field tells how many bytes may be sent, starting at the byte acknowledged. A checksum is also provided for extra reliability. It checksums the header, the data, and a conceptual pseudo header in exactly the same way as UDP, except that the pseudo header has the protocol number for TCP, and the checksum is mandatory. The option field provides a way to add extra facilities not covered by the regular header. So options field provides extended functions for TCP. Many options have been defined and several are commonly used. Options are of variable lengths. Fill a multiple of 32 bits by using padding with zeros and makes 10 to 40 bytes to accommodate the longest TCP header that can be specified. A widely used option is the one that allows each host to specify the MSS it is willing to accept. Now we will talk about TCP connection establishment. Connections are established in TCP by means of the three-way handshake discussion in the former section. To establish a connection, one side say the server, passively waits for incoming connection by executing the listen and accept primitives in that order, either specifying a specific source or nobody in particular. In other side, say the client, executes a connect primitive, specifying the IP address and port to which it wants to connect, the maximum TCP segment size it is willing to accept, and optionally some user data. The connect primitive sends a TCP segment with the SYN bit on and ACK bit off and waits for a response. When this segment arrives at the destination, the TCP entity there checks to see if there is a process that has done a listen on the port given in the destination port field. If not, it sends a reply with the RST bit on with the RST bit on to reject the connection. If some process is listening to the port, that process is given the incoming TCP segment. It can either accept or reject the connection. If it accepts, an acknowledgement segment is sent back. The sequence of TCP segment sent in the normal keys is shown in the figure 37. This is 37. Note that a SYN segment consumes 1 byte of sequence space so that it can be acknowledged unambiguously. In the event that two hosts simultaneously attempt to establish a connection between the same two sockets, the sequence of events is illustrated in the subfig B. The result of these events is that just one connection is established, not two, because connections are identified by their endpoints. So this figure shows the procedure of the TCP connection establishment. A shows establishment in normal keys. B shows simultaneous connection establishment on both sides. Now, we should understand the TCP connection establishment mechanism. In normal case, host 1 sends a connection request to host 2. Host 2 sends back acknowledgement with SYN sequence number ACK to host 1. Then host 1 sends ACK to host 2. Then a connection can be established between host 1 and host 2. although TCP connections are full duplex, to understand how connections are released, it is best to think of them as a pair of simplex connections. Each simplex connection is released independently of its sibling. To release a connection, either party can send a TCP segment with the final FIN bit set, which means that it has no more data to transmit. When the FIN flag is acknowledged, that direction is shut down for new data. Data may continue to flow indefinitely in the other direction, however. When both directions have been shut down, the connection is released. So TCP released uses the full handshakes mechanism. Normally, four TCP segments are needed to release a connection. One FIN, one FIN, and one ACK for each direction. However, it is possible for the first ACK and the second FIN to be contained in the same segment, reducing the total count to 3. Now we will not discuss it in detail. Now this figure 39 shows the finite state machine of TCP connection management. Solid line shows the client, shows the TCP in the client. The dotted line shows in the server. Now we will talk about TCP timer management. It is some complex. TCP uses multiple timers to do its work. The most important of these is the RTO, means retransmission timeout. When a segment is sent, a retransmission timer is started. If the segment is acknowledged before the timer expires, the timer is stopped. If, on the other hand, the timer goes off before the acknowledgement comes in, the segment is retransmitted. The question that arises is how long should the timeout be? How long should the timeout be? This problem is much more difficult in the transport layer than in the data link protocols. In the latter case, the expected delay is measured in seconds and is highly predictable. So the timer can be set to go off just slightly after the acknowledgement is expected. Since the acknowledgements are rarely delayed in the data link layer, the absence of acknowledgement at the expected time generally means either the frame or the acknowledgement has been lost. This figure 42, shows the probability density of acknowledgement arrival times in the data link layer. Usually, the near the 20 microseconds. Now we will not discuss it in detail about the timer management. Now we will talk about TCP congestion control. When the node offered to any network is more than it can handle, congestion builds up. The internet is no exception. The network layer detects congestion when queues grew large at routers and tries to manage it, if only by dropping packets. It is up to the transport layer to receive congestion feedback from the network layer and slow down the rate of the traffic that it is sending into the network. In the internet, TCP plays the main role in controlling congestion, as well as the main role in reliable transport. That is why it is such a special protocol. We cover the general situation of congestion control in the formal section. A key takeaway was that a transport protocol using a AIMD mechanism means additive increase and multiplicative decrease. Control law. In response to binary congestion signal from the network would converge to a fair and efficient bandwidth allocation. Figure 43 shows what happens when a sender on the faster network sends a small burst of full packets to a receiver on the slow network. That is the bottleneck or slowest part of the path. Here is fast link. This is slow link. So there is a bottleneck on the link, on this link. Burst of packets sent on fast link. Burst queues at the router and dreams onto slow link. Receive AC keys packets at the slow link rate. Then AC keys preserves slow link timing at sender. The solution Jacobson chose to handle both of these considerations is a fix of linear and multiplicative increase. When a connection is established, the sender initializes the congestion window to a small initial value of at most 4 segments. The details are described in the document RFC 3390, and the use of 4 segments is an increase from an earlier initial value of one segment based on experience. The sender then sends the initial window. The packets will take a round-trip time to be acknowledged. For each segment that is acknowledged before the retransmission timer goes off, the sender adds one segment's worth of bytes to the congestion window. Plus, as that segment has been acknowledged, there is now one less segment in the network. The upshot is that every acknowledged segment allows two more segments to be sent. The congestion window is doubling every round trip time. So this algorithm called snow start. But in fact, it is not snow at all, because it is exponential growth, except in comparison to the previous algorithm that let an entire flow control window be sent all at once, as shown in this figure. This figure 47 shows the shape of the TCP congestion control, the data rate. So the data rate of the TCP is variable with the condition of the network. This is snow start with exponential growth, then congestion avoidance, fast recovery, etc. About some performance issues. Performance issues are very important in computer network. When hundreds of or thousands of computers are interconnected, complex interactions with unforeseen consequences are common. Frequently, this complexity leads to poor performance. No one knows why. Then we will examine many issues related to network performance to say what kinds of problems exist and what can be done about them. 6 aspects of network performance, including performance problems, mirroring network performance, host design for fast network, fast segment processing, header comparison, protocols for long-fat network. These aspects consider network performance both at the host and across the network, and as networks are increased in speed and size. Then, about the other techniques in transport layer, for example, delay-tolerant networking. TCP and most other transport protocols are based on the assumption that the sender and the receiver are continuously connected by some working path, or else the protocols fails and the data cannot be delivered. In some networks, that is often no end-to-end paths. An example is a space network, as LEO satellites pass in and out of range of ground stations. A given satellite may be able to communicate to the ground station only at particular times, and two satellites may never be able to communicate with each other at any time, even via a ground station, because one of the satellites may always be out of the range. Other example networks involves submarines, buses, mobile phones, and other devices with computers for which there is intermittent connectivity due to mobility or extreme conditions. So in these scenarios, maybe special transmission protocols are needed. So about DTN, you can read the PPT files by yourself. Now, so much for today. That's all. Thank you. Bye.